Okay, looks like we are ready to get started. Let's advance the screen. And if anyone didn't see their screen advance to the next slide, please speak up now through the chat window and we will address it. Today's webinar on generative design is made possible through sponsorship from Siemens PLM, so thanks to you folks. And I don't know how many of you on this webinar have seen generative design before. I mean, I confess I'm pretty excited about it. I saw early demonstrations a few years ago, and in that short time it has come a long way. It is now commercially available within CAD systems, or at least one CAD system that I know of. So in today's presentation, we're going to hear from Chad Jackson and David Chadwick. We're going to start with Chad Jackson highlighting how and why today's engineers need assistance in design. He's going to outline what has changed in the computing landscape to make generative design more broadly available and draw out some implications of generative design for product development teams. If you've tuned into engineering.com webinars before, you will have heard from Chad. He is an analyst and researcher who provides insights on lots of technologies used for engineering and product development. So following Chad, we're going to hear from David Chadwick. He's business development manager at Siemens PLM Software, and David will show you a demonstration of generative design using an example that I saw firsthand a couple weeks ago. And I promise you that it is very informative, and although David's title says Business Development Manager, he is very sophisticated in his knowledge of engineering software in general and in generative design in particular. So, before we get started, please locate the message pane on the right side of your screen. That's where you can type in your questions. Now, feel free to ask those questions at any time during the presentation. So, when you think of them, type them in, and we will save some time at the end for our speakers to answer those questions. And as the slide says, I'm John Hayes, your host for the webinar, and I will now turn the presentation over to Chad.
Awesome. Thanks, John. Yeah, we have been on a few of these webinars together, haven't we? And I agree with you that generative design is definitely an exciting topic. You know, when I look at technologies that engineers use to design products, a lot of times there's, stepwise improvements in technologies that have been around for a while. There are certainly technologies that come out that offer an incremental value on top of what they're already doing, but I think generative design is one of these topics that it really does have the potential to change how engineers do their jobs in a great way. So that's what I'll be talking to today. So I'm going to be covering three main topics here. One is to talk to the engineer's dilemma, and I'll get more into that here in a minute, but that's going to focus on this, these opposing constraints that engineers must meet when designing products, and they're only getting more difficult. Then we'll talk about generative design and what it is and what the technology is and what the workflow in general looks like. And then we're also going to touch on FACET modeling. I'm sure a lot of you are pretty familiar with parametric modeling and direct modeling, maybe subdivision modeling, but FACET modeling is a topic that is highly applicable to generative design. So with that said, let's get started. So if you look at the landscape of design today, some things have been changing more recently. I think almost every product that's available now has an increasing amount of electronics in it, right? It also has an increasing amount of software in it. Those of you that may be on the forefront of the IoT trend also know that products now have to connect to the internet, and if you're streaming data off of sensors, well, that you got to figure out where that goes too. So the technical nature of products is getting far more complex, and what that means is if you're responsible for the mechanical aspects of a product, you got to coordinate your work with a lot of other people. I see a lot of organizations kind of transitioning over to kind of this groupthink design. It's where a lot of key design decisions are made in conference rooms, during a design review, because you want to leverage the expertise the expertise that's in the room instead of just making your own decisions. So what that means is engineers have to dedicate more and more time to coordinating their efforts with other technical designers, right? And it leaves less time for actual design, exploring alternatives, looking at iterations, and that type of thing, and finding a better design, much less a first feasible design. Now, there's another trend that is it's in parallel to this. And I'm sure many of you have kind of experienced this firsthand, but this idea that you're going to take broader enterprise considerations into account. And those considerations are only getting, there's more and more of them all the time. And what I mean by this is that you can't just look at form, fit, and function for your design anymore. You really got to take into account a lot of other issues. You got to look at cost, obviously. You got to look at how it's going to be manufactured, and sometimes you get help from a manufacturing engineer with that. But it's extending more and more downstream. You got to look at, well, how is it going to be sourced, and can I design something so it can be sourced more readily, or so that we can get parts more easily, or so, when the time comes for service parts, that it's far easier to get that, and you minimize the amount of time you have to wait for parts. You also have to think about, well, how are you going to service the part, right? How can you design something that, when a component ultimately does fail, years down the line, that it can be serviced easily and readily. So this is in parallel to the technical aspects, but these are other groups and departments and organizations in your company and maybe outside your company that you need to coordinate the design for, right? So this is another trend that is pulling engineers more away from design and the ability to explore more options. So the real takeaway here is that, now more than ever, engineers actually have less time to design their products, and that can certainly make things difficult. Now, this manifests itself in a lot of different ways. And one way this concept that engineers are doing more than they ever have before shows up in the number of responsibilities that they have. So I ran a study, a survey-based study. It was a couple of years ago now, but the whole idea was looking at titling and responsibilities and how you spend your time and that type of thing. What I found is that on average, respondents to that study had 4.4 core design responsibilities. These are things like making design decisions, managing requirements. This is, predicting the performance of products. Now, on top of that, they also had 2.9 on average responsibilities in extended design. So this is going out and meeting with customers, understanding their needs. It's going out and working with suppliers maybe on their campus and seeing what they can offer, what value can they add. This also gets into project management. So the key in all of this is that actually, the average is 7.3 responsibilities for the, average engineer, but only one of those is making design decisions. So that's just a proof point that engineers are really, they don't have as much time for design as they used to. Another way this shows up is looking at how engineers spend their time or where they spend their time. Now, certainly engineers spend a lot of time at their desks. That's probably going to be true for the most part. But they're also spending a lot of time in company conference rooms. You can see they're in the production area, which is manufacturing. You can also see they're going off-site, right? They're going to the customer's office and the supplier's office as well. So again, this is another proof point that today engineers don't have nearly as much time for design as they used to. Now, let's look at the other side of this. Obviously, there's going to be a schedule, but what is the impact of having less time to design products? Well, I know one impact for sure. This was a study this is a finding from a study I conducted a year and a half ago, something along those lines. And basically this shows that the more prototype failures that you have, the less likely you're going to be able to release the design on time, right? So that's pretty obvious, but if you have 3, 4, 5 prototype failures, it's going to introduce scheduled delays for the product development process. And that is a major challenge. And you might say, okay, well, that's not a big deal. Let's push the whole schedule back. But that has a waterfall effect on product development overall. As you can see here, this is a finding from the same study, but you can see that 25% of all projects aren't launched on time. And we all have heard anecdotally some of the impact of that, where if you don't launch your product on time, you're missing opportunities, you're going to not be first to market, you're going to lose revenue as a result. Another 20% of all projects are outright canceled. So that obviously is an issue. So projects that get delayed definitely fall into that category. 42% of all projects are launched on time but require a 10% increase or shift in resources. So engineers, stop what you're doing over here, come over, let's do the fire drill on this other project to get it out the door. That leaves only 13% of all projects that actually go as planned. So engineers are kind of in this catch-22 where they have less and less time to design, yet the implications of their work are very dire, right? If they are not successful, then it has serious implications for the company. So in that context, let's talk about generative design. So what is it? It's basically technology that augments the approach to design, right? So it helps you generate more design alternatives autonomously. Doesn't require the engineer to actually explore more alternatives. It's basically a task that you give software, and it goes off and it finds more and more alternatives for you to consider for the design. Okay, so how does it do that? Let's talk about that. One approach that is used in generative design is called topology optimization. Now basically, this is finite element analysis or simulation. What it does is it looks at the elements. If you don't remember, finite element analysis, it breaks your component down into either tetrahedrons or other smaller components and does the analyses on those. Now if it sees an element that isn't carrying a lot of load, well, maybe you don't need that material, so it removes it. So piece by piece, it can remove material that is not being used to carry a load in a structural case and tries to meet other objectives. It might be cost or weight or something along those lines. Overall, this topology optimization approach is one that is being used in generative design in general. However, there are other methods being explored, and it's early, but they're looking at the ways that nature kind of tries to achieve these same types of things. For example, if you look at the structure of bone, there are small cavities throughout bones, and through evolution, we have found the right balance between weight and carrying a structural load. Same sort of thing actually with the growth of bacterial colonies. It might sound weird, but bacterial colonies have become incredibly efficient at building redundant paths to food sources. So, some researchers are looking at that type of thing and trying to figure out, okay, well, how can we use that for structural analysis and generating more and more designs? So these are a couple of the methodologies that are being used and being put into play. So let's talk about how it works. Generative design, what's the workflow look like? Well, if you ever did the kind of parameterized optimizations from simulation, this is going to look pretty similar, at least from a workflow perspective. So first thing you need to do is basically set up your analysis. Set up your load cases. What physics is this component or design going to experience in its operating environment? So you set that up. That's your first step. Secondly, you set up your geometric constraints. When it comes to a design, there are some areas or aspects of a design that can change and some aspects of the design that can't change. So you basically, in a 3D component through a volume, you identify what can change and what can't change. The last thing you do is you identify an objective, and maybe multiple objectives, whether you're trying to constrain a weight, whether you're trying to maximize something like surface area, whether you want to make it as inflexible as possible. Maybe you want to stay away from certain natural frequencies. So you kind of set all that up and you press go. And from there, the software goes off and it starts generating alternatives. And at the end of the day, you get to review those and you kind of look at it like a design study and you figure out, okay, well, this alternative performed really well in this case. This other one performed really well. But ultimately, the decision is up to you. The software is basically doing the brute force work for you. And at the end of the day, you make the decision about the design. So what you typically see from this type of process is you have a shape that more often than not, it becomes very organic, right? It tends to follow the load path through the design. You look at those multiple alternatives and you select the one that best fits your needs. Again, you are the one that stays in control of the design. Now, what's interesting about this is that, we've talked already about how engineers have less and less time to do design work. The emergence of generative design is fascinating to me because I think it could change the structure of engineering organizations. Individual engineers could actually start to come to look like managers of many, many software agents, right? So you basically hand out tasks, okay? You go off and explore this design and generate me a whole bunch of alternatives and feasible candidates. And you might have 4 or 5, maybe 10 of those going simultaneously. And that engineer could go to the conference room. They could go off-site to the supplier's office. They could go to the customer's office, right? And when they return, they have many candidates or alternatives waiting for them to review them, right? So it's interesting to me because it feels like an extension of the engineering organization. So it's fascinating that way. It's a way to expand the bandwidth of an engineer's time for design, but to not deal with the HR issues, right? So that is one possible future. Now, something to take into account. When you look at how this technology works, it's based on finite element analysis, right? We kind of know that. And when you remove an element from that model, you're going to end up with jagged edges, right? So as you do that over time, you're going to end up with maybe something that's kind of a lumpy model, right? And when you think about that, it's actually called mesh geometry, as opposed to an exact boundary representation that is all smooth, okay? Now, you might be in circumstances where you need to make modifications or tweaks to the outcome of generative design, the outcome that is mesh geometry. And as you may or may not know, that mesh geometry doesn't have dimensions and parameters behind it to make modifications. So using parametric or direct modeling approaches really doesn't work. And this is where FACET modeling comes into play. FACET modeling provides a set of tools, almost like direct modeling, but for mesh geometry, to where you can make modifications. You can add geometry if you want to. You can modify existing geometry. You can remove geometry, adding holes and cuts and things like that. So there's been this emergence of this capability that is, to leverage generative design, you really do need it. And the best case is to have a mix of parametric, direct, and FACET modeling all within the same CAD software. So that is one important aspect to take into account. So here we go. Now, the critical thing about why you want parametric, direct, and FACET modeling in a single CAD application is to avoid translation between different applications. I'm sure if you've used CAD software before, especially in the context of collaborating with suppliers, then you know when you move geometry from one CAD application to another, you often get broken geometry that you need to fix, which in turn takes more and more time away from design. So that is one of the main reasons why you want to have all three modeling capabilities in a single CAD application. So let's wrap it up, then I'm going to turn it over to David. We talked about how, today engineers are really facing this dilemma where they have less and less time to dedicate to design, yet the impact of their decisions have dire consequences for the company overall, especially financially with their products. We talked about generative design. We talked about the concept, how it uses topology optimization, but a lot of other methods are being researched at this stage. We talked about the workflow and the technology behind it. You define the conditions that your component or design will experience in its operating environment, set an objective, and then you identify the geometry constraints that it has, what can and cannot change, and then you let it go. Ultimately, and I do want to emphasize this, engineers are under control of what the design looks like at the end of the day. Another consideration to take into account is the outcome or output of generative design is mesh geometry, and you will need FACET modeling as a means to modify that geometry. So keep that in mind as you look at generative design. And with that, I'd like to hand it over to David, and you can take it from here.
Okay, thanks, Chad. It's certainly very interesting to see some of the data from the surveys that you've conducted and some really thought-provoking comments that you have based on that survey data as well. So I'd like to start this section by giving the Siemens perspective on what we see is generative design. And the way I'm going to do that is really compare generative design with traditional design. So with traditional design, the first step that you would typically take is to make sure you understand the requirements for the design. And then you apply good engineering practices and your own experience. And typically you'd use traditional 3D CAD software to design a shape that meets the requirements. You then typically run some type of validation process on the design, typically using computer-based stress analysis and or using physical prototypes. And you may then need to loop back and modify the design. Now, with the generative design process, the first step is definitely the same. You still need to fully understand the design requirements. But the next step is to input these requirements and use software and computing power to create the best shape that meets the requirements. You still may need to do a validation process on the design, although stress analysis, as Chad has mentioned, is an integral part of the generative design process itself. So what are the steps here? Well, the first one is to input the requirements, as we've mentioned. And the first of those steps is to basically define the design space. So how big is this
component going to be? What are some of the basic parameters about the component? But then you need to go a step further and specify the geometry that is essential for the operation of this component that you're trying to design. So this could include things like locating points, bearing surfaces, and keep out areas as well. You also specify any loads, so this would include the type of load, the direction of the load, and the value of the load as well. You'd also specify a safety factor, so what factor do you want to apply to make sure that the stress in that component is significantly below the yield stress for that component. And you also need to specify what material you're planning to use for the component as well. And another parameter you can specify is a target weight as well. So then the generative design process or study kicks in, and it basically applies finite element methods and computing power to analyze hundreds of potential solutions to the design challenge. And then it offers you the optimum shape that meets these design requirements. And as Chad has mentioned, the result is a mesh or FACET-based 3D CAD model. Let's just take a slightly different direction now and look at some of the opportunities that we see that generative design offers to manufacturers. The first is the possibility to reduce cost per part by reducing the amount of material used and therefore material costs. This is particularly important for parts manufactured in high volumes, but can still have a significant impact even on batch production or even on one-off parts. The second is the possibility we see to reduce your manufacturing costs. The generative design process results in a single solid mesh body that can replace a multi-component fabrication, such as a welded assembly. This reduces your need to spend money on jigs and fixtures, and on welding materials, and on highly skilled welders. These single body parts can also be manufactured using the latest additive manufacturing techniques. This reduces the need to design and manufacture expensive tools. Another possibility we see is to reduce component weight while maintaining strength. Where the component is a moving component in a machine, lighter weight improves the efficiency of the machine and reduces energy consumption as well. And for vehicles and aeroplanes, lighter weight components also reduces energy consumption and can enable manufacturers to meet stringent regulatory requirements for efficiency of their products. So, as we mentioned, generative design is a completely different approach to design. It uses advanced software and computing power to optimize your designs. This further introduces the possibility to create radically different looking designs. The results of generative design can even be used as a source of new design ideas for your products. It tends to create unique, organic looking designs with an attractive appearance that can help your products to stand out from the competition. Now let's talk specifically about the solid edge solution for generative design. So Solid Edge, we feel, offers a unique generative design solution that enables quick creation of optimized, lightweight product designs. It uses the latest topology optimization technology for fast and accurate design optimization. It creates mesh-based solid body models with smooth surfaces that are ready for manufacturing. And very importantly, it's really embedded inside our easy-to-use, high-value, professional Solid Edge 3D CAD software. This means that you can easily develop your generative designs alongside all the components you're designing in a traditional way, or you've already designed as part of a design project. And also, you do not need a dedicated analyst to run this software. It really is a tool that all design engineers can use. We feel that a unique area of our solution is how easily it enables you to integrate these mesh-based models that are created by the generative design process into your everyday product development process. For example, you can use standard solid edge commands to add features to the generatively designed components, for example, cutouts or holes or bosses. You can align and constrain the component correctly in a solid edge assembly. And you can create 2D drawings from the 3D model. And as I mentioned earlier, you can manufacture the components using additive manufacturing or traditional machining. At this point, let's step back and just take a few minutes just to talk about the two types of CAD models that we have mentioned. So most CAD systems today use something called BREP models, and we've also talked a lot about mesh models today. So a BREP, or boundary representation model, is an exact mathematical model of a 3D part. It includes definitions of the topology, faces, edges, and vertices, and geometry, surfaces, curves, and points, with some additional intelligence to say which side of the surface is a solid. Most modern 3D CAD software today uses BREP to define the geometry of your CAD models. And then we have this idea of mesh-based models. They're also referred to as faceted or tessellated models. These mesh-based models use flat triangles to represent geometry in an approximated lightweight format. A sag parameter is used to control the approximation by defining the maximum distance between the triangle and the surface. Here you can see the dialog that you use to set this parameter for mesh models created using Solid Edge. Mesh models are created by FEA software, by reverse engineering processes, by generative modeling, by specialist mesh-based modelers, and are consumed by 3D printers and additive manufacturing. And this chart, it might be a little difficult to read, it has a lot of data on it, but it shows how common CAD formats, both neutral formats at the top and then proprietary formats at the bottom, typically use either boundary representation or mesh models, or often a combination of both. For example, IGES is a BREP format. STL, which is used to a very large extent today, one example would be to transfer data to 3D printing, is a mesh or tessellation type format. And you can see that most current CAD systems use the BREP format to define their CAD models, but many also support these mesh or tessellated formats. An important aspect of the Solid Edge approach to design is that it enables you to combine mesh models and BREP models in one environment. It does this using Siemens convergent modeling technology. In addition to supporting generative design, convergent modeling also supports reverse engineering, the process of scanning real parts to create CAD models. This process also results in the creation of mesh-based models. And for manufacturing, new additive manufacturing techniques are also based on mesh models. So at this point, let's look at a brief demonstration. So we'll show you a few examples of the generative design process, and then we'll show you step by step the generative design process for the design of a new gas pedal.
Our tour today will be looking at some of the next generation design tools, which include generative design, convergent modeling techniques, and additive manufacturing. Generative design is a process whereby the computer will create an optimized design for us based on the use criteria of the part. This allows us to ensure our components are as lightweight as possible by minimizing material usage and saving costs, all whilst maintaining the structural integrity required. The output from generative design is a mesh model. In the past, it's been difficult to work with these types of models. However, Siemens convergent modeling technology now makes this possible, and edits can easily be made to any mesh model. Let's take a look at the core area of generative design. As a quick example, we'll first take a look at this Bernina sewing machine and focus on its internal mechanical components. These components are positioned by a framework which will typically be modelled with several features which define the required geometry, all in order to make sure it's strong enough to support all the components connected to it. Now consider a process where you only design the basic shape, as you can see here, and let generative design figure out the rest. Generative design never adds material, it only removes material, so it's important to define the areas of the model that need to be preserved. Not only can you apply loads and constraints, as we're doing here, to ensure the model can withstand its standard operating conditions, but also you have the capability to select areas on the model that need to be preserved, such as mounting and locating features. Once the model's design requirements and constraints have been defined, generative design uses this important input to generate a very smooth organic shape model that fits the design needs you're looking for. Not only does generative design save design time, but also helps to reduce material costs by reducing weight. The result provides an organic, smooth mesh body ready for additive manufacturing. Generative design is useful in many different industries, including aerospace, automotive, and more. As an example, consider this simple bearing block. Using an iterative process, multiple revisions of the design can quickly be generated, helping you achieve the best possible lightweight solution for your needs, and yet still ensure it's strong enough to withstand the workloads it will face during operation. As another example, let's consider this mechanical pedal assembly. Currently, the pedal itself is an assembly made up of about 6 separate fabricated parts. This can be expensive to produce. Our interest is to reduce material, weight, manufacturing and assembly costs, but at the same time ensure structural integrity. This is a perfect application for generative design. To start with, we'll replace the pedal assembly with a basic shaped model. By moving the pedal in its range of motion, it becomes apparent how this design is supposed to work. It helps us to better understand what aspects of the part's geometry are important for the pedal to work correctly. Now we have a better understanding of how it works, we can begin to set up the generative design process for this part. We'll edit the part and turn off any background components. This lets us focus more on the design of the part itself. Generative design is fully integrated into Solid Edge, and all the commands are right at your fingertips. The ribbon presents the 10 key commands for generative design in a logical sequence, guiding the user through the steps they need to complete in order to set up and run a generative design study. First, we just need to ensure a material is defined. Once a study is created, we can then go through the process of selecting preserved regions or areas of the model we want to keep. Here we can define an offset value which will preserve the whole and the boss geometry. It's obvious where the force is to be applied on the pedal. The direction of the force can easily be set by using the Solid Edge steering wheel. The value of the force can be defined along with an offset. The final thing to do is to set the constraints on the model. For this study, we'll set a fixed constraint on both holes on each side of the bottom pocket. Again, we'll define an offset. We'll also fix the rear pivoting boss. Remember, the option to define an offset helps preserve the geometry in the part needed for it to function properly when finished. After defining all the study options, we're ready to generate the new design. The Generate dialog provides slider bars so that you can make a quick adjustment for study quality and a target mass. For this first example, we'll reduce the mass by only 20% to give us a baseline. Allowable stress values are shown as well as a factor of safety. Let's generate the model. Once generated, we can take a look at the results. Here we can see the areas of the model where the stress is most concentrated, just below the pedal. Remember though, we're still within the allowable stress for this part given our factor of safety. We can run the study again and make some adjustments. Here we'll reduce the mass a little more by changing it to 40% to see what the results look like. Immediately we can see most of the material removal occurs under the pedal. Depending on the user's preference, multiple studies can be created and each study's settings are easily accessible through the edge bar for quick changes. This iterative process to generative design makes it easy to adjust any parameters in order to get the best possible design as fast as possible. Before generating the last study, let's make a quick change by preserving the size of the pedal in order to give it more strength and stability. Once again, this is just a case of picking the required geometry and entering an appropriate offset value. This time we'll also reduce the mass of the part by 60%. Notice the result shows a huge reduction in material, and yet the super smooth mesh model has enough strength to withstand the forces it will be put under during everyday use. Displaying the background parts in the assembly gives us a clear idea how the new pedal fits within the design and interacts with the other components. The huge advantages in using Solid Edge to create and work with these generative designs, which are essentially mesh models, is when it comes to the creation of additional features that the design may need. With Solid Edge, adding and removing material is simple and fast. For example, a cutout can be added to the lower boss for the purpose of placing a bushing. The use of standard modelling tools make this process quick and easy by picking up on background parts in the assembly. We'll also add some geometry too. In this case, we'll add the part number to our part by first placing text, then extruding that text into the design. The power of Siemens convergent modelling techniques available in Solid Edge provide an engineer with the ability to further the design of mesh models fast and easy. Returning to the top level assembly, we can see the finished design of the pedal in motion with the rest of the assembly. So generative design gives us the capability to generate low-cost, lightweight mesh models that can then be modified through convergent modelling techniques. The only question that remains is how can we manufacture these models? Let's go back into the new pedal design and answer that question. Solid Edge provides the capabilities for you to take your designs directly to the additive manufacturing process. The 3D Print tab provides several options to get your designs manufactured. We'll start by previewing this model. This allows us to check on its quality and then adjust the tolerance of the facets if required. If you have access to a local 3D printer within your company, then your part can be printed right from your desktop. Here's an example of reading our design into the Fabricam 3D printer. The step-by-step approach first allows us to change the layout of the part so it's in a better orientation for printing. The Settle option uses kinematics to drop the model onto the printer bed in the best orientation. We can define the quality of the print, review any overhangs where support material may be needed, select a material, and finally make changes to advanced layout and settings. Now your in-house printer might be ideal for creating one-off prototype parts in plastic materials, but what if you don't have such a printer available or you want to choose the best material for the final part, including, for example, steel, aluminium, tungsten, ceramics or wax? Solid Edge offers the capability to order the 3D print through an online service called Through Your Mind. Through this interface you can check the printability and scale of your model, then browse through the different material options, using filters if necessary. These all include the price, print method and lead times. Once we select a desired material, we can then choose which preferred company we want to use for the actual 3D printing. The idea here is to give you all of the options needed so that you can get your parts printed as quickly and as cost effectively as possible. When you think about next generation design, think about Solid Edge and the state-of-the-art next-generation tools it offers to get your job done right first time. From generative design for creating a lightweight, very smooth mesh model, to convergent modelling, which gives you the capability to further the design and easily edit the mesh model, to state-of-the-art 3D printing capabilities.
Okay, so I just wanted to look at that last example, the gas pedal design, in a bit more detail so we can discuss some of the practicalities and the business impact of generative design. The particular customer that was doing this gas pedal design is a company called Hall Designs. They're a startup manufacturer based in San Diego, California. They actually design and manufacture custom components for off-road race cars. For example, those that compete in events like the Baja 1000. Their work has a very high design content to ensure that their components meet the extreme conditions faced by these race cars. They also manufacture, but in fairly small quantities. One feature of their workflow is that they use reverse engineering to scan existing components so that their existing components fit correctly alongside those existing components. Their design brief was to design and manufacture a new gas pedal assembly for the Herb Smith racing team. This racing team has developed a unique traction control system for their race cars that gives them a competitive advantage. The gas pedal mechanism might seem fairly straightforward, but it is actually a critical part of the traction control system, as it of course connects the driver with the drivetrain. One of the specific design goals was to replace the current gas pedal, which is actually a 4-component welded assembly, with a single body component. The welded assembly required specialist welding labor, and if not welded correctly, was subject to failure. The new gas pedal needed to be lightweight but robust, and had to be designed, manufactured and delivered in the space of 4 weeks. The solution that Hall Designs chose to meet this design brief was solid edge generative design. The key regions to be preserved for the generative design study included the footplate, the main pivot point, and additional pivots for the damper and sensor. The loads were specified, and the target weight, initially 33% of that of the original part, was entered. After the analysis was run, standard solid edge modeling commands were used to add some specific features, and the component was then aligned in the gas pedal assembly alongside other traditionally designed and reverse engineered components. A prototype was created in plastic using Hall Design's in-house 3D printer. This prototype was used to assemble the part alongside the other components to prove out fit and function, and for customer review and approval. The final production part was then created by submitting the design to an external additive manufacturing specialist. They printed the component in aluminum using a select metal sintering technique. The final component is actually 25% of the weight of the original. It has an excellent surface finish, and the high density sintering process also results in a very strong part. Feedback from Hall Design's own customer has been very positive. This is the Herb Smith race team, and can be seen in this quote. They really like the idea of not making the part in sheet metal. It doesn't have to be welded, and they believe it will have great strength and durability for their application, as well as being cost effective. Another interesting aspect of this case study is that Hall Designs is using social media to tell their customers about their use of generative design. This clearly demonstrates their adoption of the latest technology and has created a lot of interest from potential customers. And some recommendations that come directly from Craig Hall at Hall Designs are: firstly, explore and make use of new technologies before your competitors do. Then share the potential uses of generative design with your customers, and also use this as an opportunity to rethink both existing products and new designs. And from the Siemens perspective, we see that Hall Designs is using their proven capabilities in new technologies to win new customers and grow their business. So finally, just a few words about how you can get access to this technology. And the good news is there's actually a free version of Solid Edge Generative Design that includes a certain set of capabilities, a subset of the capabilities that you have seen, but it still allows you to explore generative design on your own design models. We really believe this will result in some great design ideas for you. And then the full capabilities are available in an add-on module to Solid Edge called Solid Edge Generative Design Pro. So again, the good news is you can download a trial version of Solid Edge for free. It's a 45-day free trial, and this free version does include the basic Solid Edge generative design capabilities that we've shown today. Or you can call us if you want to find out more. So that's all from me at this stage. At this point, I'd like to hand back over to John, who will conduct our Q&A session.
Thanks, David. It's good to see that demo of that part that I saw Craig Hall, he and I were talking about a couple of weeks ago. It was cool to see those actual parts live, through the various iterations that were 3D printed in test material before actually finally being printed in aluminum. So to the folks on the webinar, if you have some questions for David or for Chad, please enter them on the pane on the right, and then I'll queue them up for our presenters. The most popular question, one that I'll save you from asking, is, will there be a recording of the webinar? The answer is yes. We will send you a link tomorrow to the recording. You can share it with your colleagues if you like. There are also 2 ebooks that are available, and there is a resource pane, should be on the upper right side of your screen. Chad has authored an ebook on the next generation of design, and the folks at Siemens have created an ebook called Generative Design. So if you want to learn more about this technique, and what I think is really quite a revolutionary change in CAD software, you can download those from the links on that pane on your screen. We'll also send you a link to them in a follow-up email from this webinar, and then we'll also send you a link to the free trial of Solid Edge if you want to try generative design for yourself. There, you should also be able to see that link in the resource pane on the right-hand side. So now on to the questions. So thank you for submitting your questions. I've got some of my, there's a really good one here. It came from Chris. So I'm going to direct this one to Chad, although I'm sure David could answer it as well. Is the focus of generative design only on generating a design for 3D printing? Could you get the design to obey rules for injection molded plastics? So Chad, do you want to take a swing at that?
Yeah, sure, absolutely. So I think the answer to that question will vary by the tool that you're looking at. But there are capabilities to say, for example, you have a draw direction with a plastic injection molded part, and you need to kind of conform to that if you have a mold cavity, right? So you can actually set that up with a generative design study. I've seen other situations that do something similar with milling. So I think it depends on the tool you're talking about.
Okay, thank you, Chad. And Chris, I hope that answered your question. David, do you have anything you want to add to that, to Chad's response regarding injection molding?
Yeah, just to say that one of the options within the Solid Edge solution is some manufacturing options, and one of those is to ensure there's no overhangs in something that you design. So if you envisage manufacturing your components as a casting or an injection molding, that's an example of a manufacturing type of input that you can give to the process to make sure there's no overhangs and the component can be withdrawn from a mold correctly.
Okay, thank you. Here's a simple question. I'll answer this one. That came from from Anthony. So is the generative design, is it new for Solid Edge ST10? I know the answer to that is yes. So moving along. Thomas asks, is there a way to introduce constraints into the generative design that would make it more useful for traditional manufacturing techniques? And David, I think you just touched on that. Maybe you could expand on that?
Yeah, I'd say there are some, and I gave you the one example of having no overhangs, which would help if it's going to be manufactured for a casting process or an injection molding type process. But I'd also say that the type of models that I've seen designed so far, you could machine them on a 5-axis machine, but it would be a very expensive process to do that, I think, because they do tend to have these amorphous type of shapes, so they do really lend them to additive manufacturing. But of course, like all of you guys out there, we're seeing a huge boom in additive manufacturing right now. A couple of years ago, we had our little desktop 3D printers. You make something in plastic and it looks nice, but you can't really use it. But now, one of the capabilities we have in Solid Edge, for example, is you can upload your design to a service, and it will basically go and poll different additive manufacturers and give you quotes to make that. You can choose the material you want. It'll tell you how long it'll take to get that component. So we see that area is changing almost every day. And in the particular example that we showed you with the gas pedal, Craig has his own 3D printer, a thermoplastics 3D printer, which is great for making prototypes. But he's also started to access these external specialists in additive manufacturing as well. And within a few days, he was able to submit his component and get this really nice metal part back from actually a fairly local company that was using this sintered metal type process.
Okay, cool. Thank you. Question for Chad from John. Is there could be thousands of iterations that evolve from generative design. Are there workflow techniques that allow design engineers to group subsets of their design ideas and relate them to each other?
Good question. Again, I think this it varies by the tool that you're looking at, but in general, yeah. I mean, there are some capabilities that will track kind of KPIs or the measures that you want to track for each design iteration, and then kind of compare them. I think you saw in the demonstration, even in Solid Edge, that there were kind of different. I don't know how to describe it, I guess, and Dave, I'm sure you will, but different stopping points where you could continue and further look at further options. So I think that you see capabilities like that in the tools. Dave, you want to talk to how it works?
One of the nice capabilities you have when you submit a design study is say how long you want that to run, because you can have it run a very long time and it'll go through more iterations and might come up, and you might use this for the last step in the process, but you can also get it to run a very quick iteration. So you can say, run this very quickly. It maybe just takes 5 minutes or so to create the particular first example of the solution to your design problem. And then you also have the capability to say, okay, what weight reduction am I after? So that's just something you input. So if you go after a very high weight reduction, you might get something which looks very different to what you expect. So there's certainly a process that you go through when you're learning this technology to how you apply these different parameters that you can specify for the study. And in practice, we do find people do go through a number of iterations themselves before they understand really how the tool works best for them.
Okay, thank you. And I see we're already at 3 o'clock and we have quite a few more questions. What I'm going to say to the folks who have questions that have not been answered is that we'll share those with the folks at Siemens, and they can respond to you directly via email to the extent that those questions are ones that are germane to your decision process. Couple of things I wanted to point out before we wrap up. First off, thank you to everyone for joining us today and for your interesting questions. I wish we could have answered them all. Thanks also to our presenters, David Chadwick and Chad Jackson, and of course to our sponsors at Siemens PLM Software. As mentioned, we'll send you links to the various resources you can download, the 2 ebooks, and a link to download the free trial. As you can see, there's also a number that you can call if you'd like to speak to someone now and you have some questions that you would like answered directly. But I do encourage you to take a test drive with Solid Edge experiment with generative design for yourself. If you like this webinar, please share it with your colleagues, either via email or on social media. And if you want more information about any of the technologies mentioned in the webinar, I encourage you to check out those links as on the screen and as we will send you via email tomorrow. So thanks, everyone. With that, it's John Hayes and our team here at engineering.com signing off. Thank you very much for joining.